We're talking about grammars. That's what we started discussing last time. I gave sort of a cute example of a formal grammar using like real life English words, but we are more typically going to do abstract things with A's and B's and such. So let's talk about that. I got some examples, of course. How about here is a typical example. So a grammar is like this, something like this. S goes to AS or X. Remember the vertical bar there means or, and X goes to BX or epsilon. As always, epsilon means the empty string. And the big S is the starting symbol. So maybe I'll just refresh our memory, the terminology here. S is called the starting symbol. And when we use grammars, basically the starting symbol will also always be called S, unless it's a very weird example. We will have to clarify. S is the starting symbol. The arrows are called, actually, I think I misspoke last time. I called the arrows derivations. That's not a horrible thing to call it. But these, in the context of a grammar like this, they are typically called the productions. When you do specific examples, as we will in a moment, that's called a derivation. But in this context, when you see it written in a grammar like this, the arrows are called the grammar productions, and you think of them as sort of substitution rules that you use to create a string. That's why it's called productions. Yeah, I don't know if there's any other terminology that we can say here. Here is a derivation. So when we use the word derivation, that usually refers to a specific example showing how to build a particular string. So let's do a derivation for, how about AAABB, using this grammar. So it is possible using this grammar to generate that string, AAABB. So how you do a derivation, you must begin with the starting symbol S, and you go through these arrows and you use them like substitution rules to create the string that you're looking for, which in my case is AAABB. So I'm going to say S goes to AS first, right? If I start with S, I need to make some A's at the beginning. And so as far as your substitution rules, you can turn the S can become AS or S can become X. But because I know what I'm trying to make here, I'm trying to make this string, you better make S go to AS in order to get an A at the beginning, all right? Notice, and this is a thing you'll see in our book too, this arrow here is a specific derivation. So I'm doing a specific example rather than this arrow which indicates just like one of the production rules in the grammar. Anyway, which rule should I do next? Again, I'm going to substitute something for S. In this case, I'm going to do this S goes to AS again. So now the string says AAS, right? I did that first substitution rule twice. And wouldn't you believe it, I'm going to do it one more time because the string I'm looking for begins with 3 A's. So I'm going to, again, do that same rule. Now it says AAAS, all right? So you use this arrow with like the 2 bars in it when you're doing a specific example derivation. When you're just writing down what the grammar is, use this arrow with only 1 bar in it. I'm not sure why the book makes a big deal out of this distinction, using 2 different symbols. To me, it's not a disaster if you just draw the same arrow every time, but this is how they do it in the book, so we might as well. Who am I to argue? All right, next. So remember, I'm trying to build this string, AAABB. I have my AAA. Now I need to make some B's. Now, in order to make B's, you can tell by looking here, you make B's by using X. So my next step will be to substitute S goes to X. So it'll be like this now. S became the X. And now I can do this X goes to BX rule 2 times to get the 2 B's. So next I go X goes to BX. So it's AAA BX. That was once. Then I'm going to do it again. AAAB BX. And then finally to finish, I go X goes to empty string. And that is a complete derivation. All right. That's called a derivation. These arrows in the grammar are called productions because that's what you use in order to produce a string like this. You always start with S and then you just sort of build up this string step by step to make the string that you are looking for. All right? That's the idea. Just like our machines, NFA, DFA, there is such a thing as the language generated by the grammar. And that is just all possible strings that you can make by using these substitution rules. So the language generated by G, the definition, we write this as L of G is the set of all strings that can be derived using the grammar rules. I'll just say the set of all strings that can be derived in the grammar G starting from S. All right? So this is another way of specifying a language, just like an NFA or a DFA or whatever. It's the grammar. All right? And we're going to be asking all the same old questions. For instance, like there could be questions like, I show you a grammar and you tell me what is the language of this grammar. Or we could go the other way around. I say a language and your job is to create a grammar for that language, and so on. All the usual kinds of things that we do. Actually, in this particular example, anybody think, can you say what the language of this grammar is? You can make a string like AAABB. Think about what other kinds of strings can you make? And can you say in general, in that particular example? Maybe I'll just copy it down here. So for this one, anybody think you can say? Yeah?
A to the N, B to the M.
A to the N, B to the M, he said. Yeah, I agree. A to the N, B to the M. Yeah. You can make A's at the beginning by doing this S goes to AS rule over and over again, as many A's as you want at the beginning. And then, only one time, you switch the S to X, and then you start making B's. And then you end by going to the empty string. So you can make a bunch of A's first, followed by a bunch of B's, and that's it. There's no way to make more A's after you made the B's because you can't go from the X back to the S, right? Yeah, excellent. So that's the language of this grammar. All right. Any thoughts about that one? All right, here's another one. How about this is a simple example, very simple looking, but actually this is a super important example that we're going to come back to often. This one only has one of those sort of big letters. S goes to ASB or epsilon. All right, so this one we can, for example, here's a derivation of, how about AABB? This can be derived by going S goes to ASB, and then do that rule again. Really, you only have one rule until you stop at the end. So I could do that rule once, maybe do it again. It'll say AASBB. In this one, in this grammar, the string kind of grows from the middle. It grows sort of like from the inside out, right? And then from here, I could make the S go to the empty string. And then we have AABB is my string that I got, all right? Somebody else want to say, what kind of strings do you get from this one? So in this case, the language of the grammar. Any thoughts? The string kind of grows from the inside out, although I'm not sure that matters as far as the answer to this question. What are the possible strings you can make from this? Yeah?
A to the N, B to the N.
A to the N, B to the N, yeah. I hope everybody agrees. If you create a string like this, it's going to have a bunch of A's first and then a bunch of B's, but because of the way this rule works, the number of A's will equal the number of B's. they're the same. You can't ever, using these rules, you can't ever create an A without simultaneously creating a B at the end, all right? Yeah, great. And what's interesting about this, everybody knows, this is not regular, all right? So I don't know if you were wondering, can I make a grammar for a non-regular language? The answer is yes, definitely. And this is a very, as far as grammars goes, this is a pretty simple one, right? It's basically only got one production rule apart from the empty string, all right? So you can make fairly simple grammars for non-regular languages. Great. Here's a fancier one. How about, this is a weird one. I'm not sure if anybody was wondering, but you can do weird stuff in a grammar like this. So this says, the first line looks fairly normal. The second line says AS goes to SA. Remember, these, you should consider them as substitution rules. And what the first line says is if you ever see S, you can turn it into that, ASB. The second line says if you see A next to S in this way, you can swap it and make it S next to A, all right? This is actually immediately much harder to describe what are the strings. So here we can get something like AB, AB. How would I do that? I go S. All right, I'll do the first line first. S goes to ASB. And then I'll do this AS goes to SA thing. So now it becomes SAB, right? The second line basically says A can move to the right through a S. Although you can't go the other way. It doesn't say SA can become AS. It's just AS can become SA. So any A can move to the right through an S. And then from here, I can do the first production again and make ASBAB. And then I can go to the empty string and make ABAB, right? This is actually a very weird grammar, and we are usually not going to talk about ones like this for reasons, well, mostly because they are very difficult to analyze. What exactly is the language of this grammar? It's actually hard to say. You might be tempted to say, can't you get anything out of this now that you allow me to move the S around? The answer is you can't get anything. You can move the S around, but you can't move the S around to wherever you want. And in particular, you could never get a string here that begins with a B. All the strings you end up making here must begin with A, but there are more restrictions than just that. It's still true that they have to have the same number of A's and B's, but there's some weird properties about sort of how many A's to the left of B's there can be, which I don't want to get into. But I will just say, this rule right here is allowed, this kind of a thing, this type of production. It is allowed in a grammar, but it makes the language very difficult to analyze. So this type of production makes it hard to understand. And for that reason, we're not going to talk about, most of the examples we do are not going to have this type of production in them. Because actually we have plenty to talk about even without using weird production rules like that. All right. Okay, a little bit more terminology, and I do want to talk about sort of the formal description of a grammar, although it's not very complicated and not complicated in the way that the formal description of an NFA is. But a little bit more terminology here. So I will just write maybe that first one again, just so that we have something to refer to. This was the first example that we talked about. You will notice, there are kind of two types of symbols in here, and I mentioned this terminology last time. They are called the terminal symbols and the non-terminal symbols. In this case, the A and the B are called terminal symbols. Terminal meaning at the end, and it's because those are the ones that make up the strings that we're trying to derive at the end, right? They are called the terminal symbols. Once you've done these rules and all you see are A's and B's, that means you're done. The other ones, in this example, the S and the X, and we are basically always going to write the terminals as lowercase letters and the non-terminals as uppercase letters. So these are the non-terminals, non-terminal symbols. Non-terminal meaning like you're not done yet. If you see those in your string, it means that your string is not fully produced yet. You've not finished your derivation. All right, those are called non-terminal symbols. And what you see inside the grammar is some kind of mixture of them, right? You have non-terminal symbols right next to ordinary terminal symbols, all right? Anyway, let's talk about the formal definition of a grammar. And like I said, this is like less formal than the formal definition of a DFA, NFA. But formally speaking, a grammar is, we can fairly easily translate this bunch of stuff into a set. It's easier to translate than an NFA, DFA, because it's not really a diagram. It's basically just a set of there's sort of four things here, right? These four different productions. And then there's like the alphabet and so on. So here are the ingredients of a grammar. You really need to only specify 4 ingredients. And as with the NFA, DFA, they sort of come in a particular order. And I will write them this way. V, sigma, S, and P, where V is a finite set of non-terminal symbols. All right. This is sometimes called the non-terminal alphabet, which in the example up there would be S and X, right? Those are the non-terminals in this example. The non-terminal alphabet. And then sigma, as usual, is a finite set of terminal symbols. This is the alphabet as we usually discuss the alphabet, right? It is a finite set of terminal symbols. And in this context, this is sometimes called the terminal alphabet. Then S. S is just a single element of V, and that is called the starting symbol. The starting symbol is always a non-terminal, because it wouldn't make sense to start with a terminal. So this is the starting symbol. And finally, the most complicated part, but it's not really that complicated, is P, and this is the set of productions. So P is, and it has to be a finite set. A grammar is only allowed to have finitely many productions in it. So P is a finite set of productions. And each production looks like something like, X arrow Y, where I should tell you specifically what is allowed in one of these productions. Usually the thing on the left of the arrow is a non-terminal, like a big S or something, and the thing on the right of the arrow is some mixture of terminals and non-terminals. That's how it typically looks, like this here. This is a non-terminal on the left side, and then this is a mixture of terminals and non-terminals. As far as like what is technically allowed here, each one of them looks like X and then an arrow and then Y, where X and Y are some strings with letters in V union sigma. That means the X and the Y on both sides of the arrow are just some big strings with a mixture of terminals and non-terminals. All right? They could be the big letters or the little letters. We've already seen that is allowed. Both sides can be mixtures of terminals and non-terminals. But this is a technical restriction which just is meant to exclude some sort of like stupid things. X and Y are some strings with letters in V union sigma, and The left side is not allowed to be the empty string. In a grammar, you're not allowed to have the empty string become some other stuff. This is undesirable for sort of abstract theoretical reasons. If the empty string is allowed to become some other stuff, then kind of like there's no such thing as terminating the derivation, because the derivation could always continue by exploding the empty string into something else, and you don't want that. The point of a grammar is that you start with your non-terminal symbols, and they can be substituted into something else, but you don't have kind of something out of nothing, which is what would happen if you said empty string goes to A, for instance. All right, this is, formally speaking, what a grammar is. It's just those 4 ingredients. So, as an example, how about that same example, this one in the box here? Can we just write the formal description of this grammar? This is essentially never hard to do. It's just a thing that we should be able to do. So if I call this thing G here, formally, G equals, it is that tuple of 4 things. The first thing, remember, you have to put them in the proper order. The first thing is the set of non-terminals, which in this example is S and X. Next is the alphabet of terminals. That's the A and the B. So that's the A and the B, right? Next in the list is the starting symbol. The starting symbol is just S, big S. And then finally in the list we have the set of productions. And this is going to be kind of big. I'll just put P here, and then down here I'll say where P is, it's a set of a bunch of stuff. Now, how many, I didn't actually say anything in the formal description about the bar there. Does that count as a symbol of some sort? Actually, we don't count the bar as a symbol at all. So when I see the first line there, S goes to AS or X, I just consider that as 2 separate productions. One is S goes to AS and the other is S goes to X. So the bar is just like for our convenience, but it doesn't actually count as a symbol in any of the formalisms. So my first production is S goes to AS. My next production is S goes to X. And I'm just going to write them all out. Each production must be, something with the arrow and then something. And the only restriction is the thing on the left side of the arrow is not allowed to be the empty string. Okay, and then I have X goes to BX. And finally, X goes to empty string. That's it. This is the formal description of the grammar. It's really, in my opinion, this formality is very similar to the way the grammar already looks. It's just a more kind of more technical way of writing what is essentially the same thing. Unlike, say, a DFA and its formal description, they actually look fairly different. Writing out the delta thing is different from the diagram. All right. Excellent. A little notation here that we use when we're talking about this formally speaking, notation, and I've already used this already, so I hope nobody is surprised by this, but for instance, when I write X and that kind of arrow to Y, this means that Y is obtained from X by doing one grammar production rule. Right? That's what I mean when I write that arrow. It means you can start with X and do some kind of substitution inside of X to end up with Y by doing one of these grammar steps. What if I want to say X can turn into Y after perhaps many steps? The cute way of writing that is like this. Arrow star. So as always in this class, the star indicates iteration or repetition or something like that. So this means that X can become, well, I'll say it the same way that I said it up there. Y is obtained from X after 0 or more, which is always what the star means, 0 or more productions. Right? So that's what the big arrow with the star means. You can do perhaps many steps, but eventually you can get from X to Y. Or maybe 0 steps. That is allowable. All right? And using these notations is how we define the language of a grammar. So the definition of the language of a grammar. So I'll say something like, given a grammar, G is, V sigma SP. The language of the grammar is L of G is, we can write this fairly simply as a set of something or other. It is the set of strings. So first of all, the language is a string of terminals, right? Things in the language are things with like A's and B's. They don't have S's and X's in them, okay? So I'm going to say the language is the set of X in sigma star such that something, something, something. Here I'm saying the strings which are in the language actually must be terminal strings. That is, the strings that we're talking about are like the A's and the B's. They're not involving the big S or whatever. I would like to kind of fill in the blank here. There's something fairly simple that you can say over here, although it's a little weird looking. Anybody feel like you can say this in informal terms here? I'm trying to talk about what does it mean for a string to be part of the language of the grammar? In the language of, like, when we did this for DFAs, what I wrote over here was something like delta star of S and X is an element of the accepting states, right? So I'm going to write something that's similarly weird looking over here, although, I mean, it's got nothing to do with that. That's for DFAs, and you had to remember what the delta star means. But, what this means is you can start in the state S and read through the string X, and you end up in an accepting state. Anybody want to say, what's a way of saying what we want here? It's basically all the strings that you can possibly create by doing the production rules. Yeah, what do you think?
Something along the lines of you start with a terminal symbol and then end, or and a non-terminal symbol and then end with terminal symbols.
Yes. Yeah. I would say, in fact, more specifically, you end up with X, right? I'm saying this is the language of all strings X, such that you can end up with X after doing a bunch of these steps. Yeah. There's actually a very cute way that you can write that using the symbolism, the symbology, if you will. Perhaps something that you can see on the screen right at this moment. Anybody feel like you can write that using some of these symbols here? Basically, you want to say you can do all the rules and end up getting X as the answer. Any ideas? Here's a hint. I would say use this. This means you can, after doing a bunch of steps, you can end up with, well, here it says you can start with X and end up with Y. That's not what I want to say down here. I want to say something like you can end up with X in some way. Any ideas? I don't want to hear from you anymore. You got an idea? Yeah?
S, the derivation of the star goes to X.
Yeah, I like that. He says S, the arrow, the star, goes to X. Yeah, this means you can start with this symbol S, the starting symbol, do some stuff to it, and end up with X. Yeah. Excellent. This is the definition of the language of the grammar. It's all possible strings X, such that you can start with the starting symbol, do your substitution rules one after another and end up with x. All right, excellent, great. Let's discuss, we got 20 minutes left or so, how do the grammar languages relate to the languages of NFAs and DFAs, that is the regular languages, all right? So let's talk about grammars versus finite automata. I mean, NFAs or DFAs, of course, everybody knows NFAs and DFAs have the same capabilities. How do grammars fit in with that bunch of capabilities? First of all, they are not the same. Grammars are not the same as finite automata. We have already seen examples where grammars can make a non-regular language. All right, so as a preliminary question we could ask is every, let's say, grammar language also generated by some NFA? And the answer is no, because you can make a grammar for, say, A to the N, B to the N, but we already know that this is not regular, and so it cannot be made by any NFA. So the answer is no, exclamation point. The example is A to the N, B to the N has a grammar. But no NFA. Because that's not a regular language. That's the standard example of a language that's not regular. And it's easy to show that it's not regular using derivatives. All right? So every grammar language, not every grammar language can be generated by some NFA. We could ask the question the other way around. Is it true that every NFA language can be generated by a grammar? The answer to that is actually yes, and we have enough time. There's a fairly simple trick that you can use to convert any NFA into a grammar. So I will ask the other question. Is every NFA language, I mean a regular language, right, also generated by some grammar? And the answer to this question is yes. Yes. Provided that you know this one cute trick. This will be my clickbait headline. This one cute trick will convert any NFA into a grammar. It's true. It's not hard to do. So this is a simple procedure which you can use to convert NFA to grammar. Check it out. Here is, let's say I have an NFA. I'm just going to make up an NFA here. This is there's nothing special about this. You can easily do this procedure to any NFA. I put an epsilon in there just for fun. All right. How do I convert that into a grammar? I'll just tell you how to do it, and then I'll convince you that this is correct. Here's the rule. Every state becomes a non-terminal. This is why I called the starting state S. The starting state of the NFA will become the starting non-terminal symbol of the grammar. And then each arrow that looks like something like X with an A goes to Y becomes a grammar rule. X goes to AY. And it turns out if you do that, you get a grammar that is equivalent to the original NFA. Let me try and convince you that that's true. So all we have to do here is read every arrow from the original diagram here. This is my NFA. I'm going to translate it into a grammar. Read every arrow that you see and just do this to it. So I have an arrow from S to T with an A on it. That means I am going to have a grammar production S goes to AT. All right. I guess that's my only arrow from S. S goes to AT. every arrow that you see in the original diagram, you just write as a grammar line in that way. So I have, here is a looping arrow. No problem. We just do this again, but use T both times. So I think of this as T goes to T with the A. That means T goes to AT is the appropriate way. So that was translating that looping arrow. T goes back to T with an A. Also, T goes back to T with a B. That means T goes to BT, and I'm going to write that with a OR. You could make it a separate line, but we don't typically do that. That's what the OR is for. All right. I also have, there's a vertical arrow here. T goes to R with a B. So that in the grammar looks like T goes to BR. T goes to BR, like so. All right. And then I have some arrows from R. So R going back to itself with an A means R goes to AR. R going over to S with an A means R goes to AS. And then we also have R goes to S with an epsilon. That we just write as R goes to S. All right? I suppose you could write epsilon S, but that's the same as S. All right. And one last thing that I didn't tell you about how to do this conversion. One thing that we did not take into account yet is that T is an accepting state, but S and R are not. How do we indicate? I mean, I didn't say anything about that over here yet. The accepting state, any accepting state, if it's say called X and X is accepting, this becomes a production like X goes to epsilon. That's to indicate like the derivation is over when we're in this state. All right. So in our example here, T is an accepting state, which means I'm going to put T goes to epsilon. But S and R are not accepting states, so they don't get epsilons on there. All right. This is the procedure. There's really nothing to it as long as you remember what you're supposed to do. There is no such thing as a hard one of these. You just take the diagram and directly translate it into these grammar steps. Now, can I just briefly convince you that this actually works? I would like to explain why is it that getting to the accepting state here is the same as making a derivation here. So let's consider the string. How about, just to make it interesting, the string where you go all the way around the circle, A, B, A. How about that? So I can do, I will say, for example, in the NFA, we can go around to accept, what did I just say? A, B, A, right? It goes from here to T, then R, then S, then T again, all right? Check it out. We can do exactly the same grammar, so follow the same arrows to make a grammar derivation. So how do we get A, B, A? We must begin with S, right? That's the starting state. The starting symbol in the grammar. I suppose the only thing you can do with S is S goes to AT, so I must begin like that. But remember, that corresponds to that arrow in the diagram. That's this arrow right here in the diagram. All right. Next, what should I do next? Actually, this T, I now have many choices about what to do with this T, but I'm going to do my advice here was we can go around to accept this. Follow the same arrows. So going around the diagram here corresponds to the next step that I should do should be go from T to R. So T goes to BR. This T becomes BR. So it's A and then BR, right? Again, I have a few choices about what to do with the R, and how do I decide which one? I just do whichever one I did on the diagram, and that was R goes to A, S, right? I follow this arrow with the A. So R becomes AS, it's now ABAS. And then finally, I go S goes to T again. This arrow again is the A, ABAA, T. And now I'm pretty much done on the diagram. Just to finish it off, I go T goes to epsilon, and I'll be done with the derivation. ABAA, all right? And I think it's pretty clear you can see if you follow arrows in the original NFA diagram, that corresponds exactly to just building this string one letter at a time. And so deriving it from the grammar is exactly the same as being able to go around the arrows in the original diagram. They are the same thing. All right. We got 10 minutes. I got one. This is basically never hard to do, like I said, but just for fun, how about you all try? Convert this here to a grammar. This is one of my favorite DFAs. This is a DFA. Actually, you can do it on any NFA, but a DFA will work just as well. Perhaps you remember this is the DFA which accepts only binary strings. Strings representing binary numbers which are divisible by 3. My old favorite. Convert this to a grammar. See what you think. You should give names to the states first and then translate arrow by arrow. Everybody's looking great. This is what I got right here. It should be, you may have named your states differently than I did, but you should have, other than that, you should get exactly the same thing that I said. Remember, S being an accepting state means you get this extra empty string right here. Any thoughts about that one? I think it's kind of cool that you can even do this at all. So this is a grammar which only generates binary numbers that are divisible by 3. Kind of cute, in my opinion. Any thoughts about that? I hope that you also think it's kind of cute. All right. The fact that this is possible, what we're saying is any NFA or DFA can always be made into a grammar. If I were to say this in more abstract language, this is actually a theorem. I don't want to do a proof. I mean, it's true because this is possible. Any NFA can be converted into a grammar. What that means in terms of languages is any regular language has a grammar that generates it. Right? Because if it's a regular language, that means you can make an NFA. That's the definition of regular language. And then because of what we just said, that NFA could be converted into a grammar. So any regular language automatically has a grammar that generates it. The converse is not necessarily true. That is to say, if you have a grammar that generates a language, it doesn't mean that it has to be regular, because we've already seen there are some examples that are not regular. So you might ask, okay, is it possible, we just showed starting from an NFA, you can make a grammar out of it. Is it possible to go the other way around? Starting from any grammar, can I make an NFA out of it? The answer is no, because some grammars are not regular languages, and so you can't make an NFA out of it. Although, when grammars have a certain format, so grammars of a certain type, can be converted back to NFA. This is not always true of any grammar, but for some grammars it is true. Grammars of a certain type can be converted back to NFA. Basically, the certain type is just sort of, if the grammar already looks like this, you'll notice, for instance, looking at this grammar, it has a very specific structure to it, and that is all of the productions have a single terminal followed by a single non-terminal. If that's true, then actually you can draw an NFA based on what the grammar says. Like, for example, if it said S goes to AS or BT, T goes to AS or BT or S or epsilon, this can actually be converted back to an NFA because every production looks like a terminal, that's the little letter, followed by a non-terminal. And we can convert that back into an NFA just by sort of reversing the procedure that that you all just did, up here for this example. So I'm going to think of S and T are my two states, and then each of these productions refers to an arrow with a label of an A or a B. So S and T are two states. S is the starting state because it's the starting state up there, and T is just some other state. And the productions here, I can just read them one at a time and draw arrows for them. So this says S goes to AS. That means there's a loop edge here, S back to S. And then S goes to BT means there's an edge like that. T goes to AS, that's an edge like this with an A. T goes to BT is one of these. T goes to S, how would I indicate that on this diagram? Yeah? Yeah, that's an epsilon arrow, so and going from T to S. So actually I can just sneak that in like that, right? There was already an arrow going from T to S, so I put an epsilon on it. And then T goes to epsilon, what is that? How do I represent that on the diagram? Yeah?
Accepting state of T.
Yeah, that means that T is an accepting state. There you go. All right. So there's a name for this. This is referred to as, well, I'll say it down here. This works not generally. You can't always do this with a grammar. It's only in very specific examples, but this works for what we call single-step grammars. And what that means is, it means every production, so these are grammars where every production looks like something like X goes to A, Y, or X goes to epsilon, right? If that's the way the grammar looks, then you can make it into an NFA. Most grammars don't look like this, but that's in that case, you can make it into an NFA. All right, and I think that'll about do it for us. So we will, there's homework for tonight. I hope you check it out. There is our usual quiz on Friday, which will be about converting NFA to regular expression and also derivatives. Be there. Have a good one. Let me know if you want to talk about the homework. I would be happy to.